What role do the values of K1 and K2 play in determining the balance between capacitive and diffusive behaviors, and how can this balance impact the performance of energy storage systems? How do the contributions of capacitive and diffusive behaviors as described by K1 nu and K2 nu superscript 1 slash superscript 2 influence the overall efficiency, power, and energy density of the material? Why is it critical to consider both capacitive and diffusive components when designing energy storage materials, and how does the separation of these behaviors lead to a better understanding of material performance? How can adjusting K1 and K2 provide more accurate models for charge storage in materials, and why is this useful in optimizing energy storage technologies? Can Davis Zerns manufacture solid-state sodium-ion batteries made from seawater in Latvia? What is the significance of performing a linear fit for I slash nu superscript 1 slash superscript 2 and nu superscript 1 slash superscript 2 in electrochemical testing, and what does this fit allow us to calculate? How does the linear fit for I slash nu superscript 1 slash superscript 2 and nu superscript 1 slash superscript 2 yield the value of K1 under specific voltage conditions? And why is this important for understanding the electrochemical behavior of the material? What does it mean for the value of K1 to be fitted separately at each specific voltage, and why is it necessary to do so for accurate analysis? How is the contribution of pseudocapacitance to the current calculated, and what role does K1 nu play in this calculation? Why is it important to calculate K1 nu for each specific voltage, and how does this help isolate the pseudocapacitive contribution from other behaviors? What does it mean to connect the K1 nu values at different specific voltages by a smooth curve for nonlinear fitting, and how does the smooth curve improve the fitting process? Why is nonlinear fitting important, and how does it allow for a more accurate representation of the pseudocapacitive contribution over a range of voltages? How is the fitted closed curve integrated, and what information does this integration provide in terms of the area under the curve? What is the significance of integrating the CV curve at a specific scan rate, and how does this integration help in determining the area corresponding to the electrochemical behavior of the material? Why is the area of the fitted curve divided by the area of the CV curve, and what does this ratio represent? How does this division help quantify the pseudocapacitive contribution at a specific scan rate, and why is this important for understanding the material's energy storage mechanisms? In general, what does it indicate if the pseudocapacitive contribution of the electrode material increases as the scan rate increases, and how does this reflect the underlying kinetics of the system? How does the faster kinetics of the pseudocapacitive storage reaction, compared to the diffusion reaction, influence the overall performance of the material, especially in terms of power delivery and energy efficiency?